so now it's time to introduce the transformer. So the transformer was introduced in this paper 2 years ago. The paper is called Attention is All You Need. And you can get an intuition here that it will be strongly based on the idea of attention. The transformer paper, it uses many interesting points to make this architecture very efficient and to work so well. And unfortunately, we don't have the time to go over all these points, so I will quickly mention some of them, but I will focus in the two in particular that we really are interested in, which is the part that will substitute the RNN. But before going there, you can see here on the right the transformer architecture. So you can see it's somehow complex, but you should be able to spot the familiar architecture encoder-decoder. So you see the component on the left. This is the encoder that will run over the input sequence. And this component on the right, this will be the decoder that will produce the output sequence. We mentioned before that we want to keep three things for the sequence-to-sequence plus attention model. The encoder-decoder architecture, which you see here, the attention mechanism, and you can see it here. So here you see the multi-head attention that is going from the encoder to the decoder, so that the decoder can look back exactly as we did with the sequence-to-sequence example before. And actually, you see that that attention is used also in other points. So you see it used here and here as well. And this is the part that we will see more in details in the rest of the presentation. The third point that we mentioned, we want to keep the autoregressive nature of the decoder. And you cannot see this from the picture, but I can tell you that it is still there. So the decoder still runs in this autoregressive way. So here you have the key points from this paper with respect to this architecture. And the first point is the one that we are really interested in. So the RNN will be replaced with self-attention and multi-head attention. We will see these two techniques in the next slide. Other things that I will just mention, but I will not go into details. So they also use positional encodings. So this is some way to understand the position of the words in this architecture. So it gives more information about the position. They also use residual connection. So this is exactly what you saw yesterday with the CNN. And the reason why we use residual connection is that you see that here this architecture, the transformer, there is this N here, NX, which basically means I can have several layers. And actually, they use many layers. Like I think in the original paper they used 12, but today we can use 24, and there are definitely architecture with more than 24. And that means that the gradient has some difficulty in flowing in this very complex architecture. So exactly as we did yesterday, we use this residual connection that you see here to allow the gradient to flow more easily. There is also layer normalization. So you have seen yesterday batch normalization. So we were normalizing with respect to the batch dimension. Here is the same idea, but we are normalizing on the layer dimension, so on the time dimension. And they also use this position-wise feed-forward network, which basically means that they have an MLP that they can use on every element, and the intuition here is just that it gives more flexibility to the model. But the two really interesting points are this self-attention and multi-head attention that we will see now.